The universe speaks to us in whispers, impulses of energy that traverse the vast expanse of space. Some of these whispers we understand, while others remain elusive, shrouded in mystery. Beyond the shimmering galaxies and the twinkling stars lies a question that has baffled astronomers and scientists alike. Today, we turn our cosmic ears to one such enigmatic whisper, a signal known as GPMJ 183910. Join us on Mars 666 as we listen closely to the universe's secrets and explore the depths of this cosmic code. Astronomers have stumbled upon something they have described as an enigmatic transient object. This celestial enigma, now known as GPMJ 183910, had a peculiar habit of appearing and disappearing, almost like a cosmic magician, emitting energy 3 times per hour. But it wasn't until 2022 when a team from Curtin University, while using the powerful Murchison Wide Field Array radio telescope in the outback of Western Australia, took a closer look. That's when they began to suspect they were dealing with a long-period magnetar, one of the most extreme objects in the universe. Team lead Natasha Hurley-Worker expressed their awe, saying that this remarkable object challenges our understanding of neutron stars and magnetars. It's worth noting that this is only the second long-period magnetar ever discovered. The first one, believe it or not, was found by an undergraduate student, Tyrone O'Doherty. Now, the astronomers did not stop there. They decided to take a leap into observational logs from other radio observatories spanning decades. And what did they find? This mysterious object had been quietly observed since 1988. It's just that no one had a clue about its true nature. Imagine that. It had been hiding in the data for 35 years, completely unnoticed. The team embarked on follow-up observations, utilizing radio telescopes in Australia, South Africa, and even the XMM Newton X-ray telescope in orbit. The object showed up in the radio telescope data and even in infrared observations from a telescope in the Canary Islands. But the data suggested that this enigmatic object doesn't emit X-rays. Now, here's where it gets even stranger. Hurley-Worker explained that this cosmic oddity, known as GPMJ 183910, is spinning too slowly. It's spinning so leisurely that, theoretically, it shouldn't be sending out those radio waves. You see, periodic radio emissions from magnetars usually occur because of their fast spins. Considering it could be a magnetar, the conventional wisdom would rule out the possibility of this object generating radio waves. However, contrary to expectations, it's doing just that. And it's not a mere blip of radio emission we're talking about. Like clockwork, every 22 minutes, it unleashes a 5-minute burst of radio wavelength energy, a phenomenon that has persisted for a staggering 35 years. The mechanism driving this remains nothing short of extraordinary. It's not unusual for astronomers to capture and observe repeating signals. They often originate from pulsars, neutron stars that send powerful pulses of light across the cosmos as they spin. The location of this enigmatic source, called GPMJ 183910, lies a staggering 18,000 light-years away. Its signals arrive as pulses, but here's the twist: these pulses can last anywhere from 30 seconds to 5 minutes, repeating after every 20 minutes. To us, this might seem like wild variation, but in the world of neutron stars, things can get incredibly complex. Now, neutron stars are the leftover cores of massive, dead supergiant stars. These incredibly dense objects are like no other in the universe. Picture an entire star composed solely of neutrons. No electrons, no protons, just pure, mind-boggling density of neutral atomic particles. Even a teaspoon of neutron star matter would outweigh 11 times the entire human population. A typical neutron star is about 35% more massive than our Sun, packed into a sphere no larger than Manhattan Island. But the real star of the show is its magnetic field. an astoundingly powerful force that defies explanation. So, how do pulsars, including neutron stars, create the mesmerizing light that reaches our telescopes? It all begins near the magnetic poles of these cosmic behemoths. An electron gets accelerated by the magnetic field and emits a curvature photon. This marks the start of a pulse, and the photon moves in a straight line until its momentum deviates too far from the magnetic field line. When that happens, the photon dissipates its energy into a quantum field of electrons, giving birth to an electron-positron pair. These pairs then generate synchrotron photons, setting off a cascade of exponential growth, creating an intense beam of light that reaches us across the vast cosmic expanse. But here's where it gets intriguing. Neutron stars aren't perfect cosmic lighthouses. Their magnetic poles rarely align with their axis of rotation. Picture a beacon sweeping its light around the universe as the pulsar spins. We, here on Earth, perceive this as pulsating light. These pulsars are in the radio part of the spectrum, which means only a radio telescope can detect them. And not only are they pulsating, but their light waves are polarized, aligned along the same axis, a telltale sign of neutron stars. So, by now, you might be thinking, this sounds like a classic pulsar story. Right, well, not quite. You see, pulsars are cosmic timekeepers, but their stability is expected to decrease as they lose energy over time. As they slow down, they eventually reach what's known as the Death Valley, where their beam should fade into darkness. But our signal defies this logic. Astronomers, armed with decades of data, calculated that the source rotates once every 21 minutes and 58 seconds. Surprisingly, this rotation period has remained unchanged for over 35 years. It is a minor change, a mere 0.28 milliseconds over the entire period. That's unheard of for a pulsar rotating so slowly. The combination of such a slow rotation rate and incredible stability challenges our understanding of neutron stars. As pulsars lose energy, they should slow down, power down, and enter that dreaded Death Valley. But our signal shines bright, in defiance of the cosmic laws we thought we understood. So, what could this 22-minute enigma truly be? The astronomers who discovered it have put forth a few tantalizing theories. Could it be a magnetar, a neutron star with an incredibly strong magnetic field, undergoing cataclysmic starquakes that temporarily reignite its beacon of light? Or perhaps, it's a highly magnetic white dwarf, an uncommon remnant of a star's death, with a field stronger than any seen before. But none of these theories seem to fit entirely. Magnetar outbursts should emit X-rays, and our signal has persisted for over 3 decades. Beyond the lifespan of such phenomena, white dwarfs, even with strong magnetic fields, fall short in matching the signal's strength. So, where does this leave us? The truth is, we're in uncharted territory, my fellow stargazers. This mystery, as perplexing as it may be, is precisely what excites astrophysicists. It challenges our long-held beliefs and beckons us to explore the cosmos with fresh eyes. We have ventured deep into the cosmos, unveiling the perplexing tale of GPMJ 183910. GPMJ 183910 is just the tip of the cosmic iceberg. Similar signals may lurk in the depths of our galactic plane, waiting to reveal their secrets. But remember, this is just the beginning. The universe extends an open invitation to explore its countless secrets. Join us on Mars 666 for more journeys into the unknown. Until next time, keep your curiosity alive, for the cosmos holds infinite stories yet to be told.